Okay, nice. So today we are going to study chapter 4. Okay, chapter 4. So the last chapter of wave optics. So I think starting from week 5 or week 6, you will have this quiz. You will have this quiz 1. So it will cover all the chapter on optics, or both wave and the geometry optics. So this is, I think you have to start preparing for the quiz now. As I said, the quiz is just 6 MCQ, so to be solved in 30 minutes, So normally 5 minutes on each, I think time should be enough. So for today's class, we are going to learn a diffraction of light. So for diffraction of light, so we have a lot of content to go through. So you can say my summary is no longer just the simple 2 or 3 slides, or just the 2 or 1 table for you to remember. Here we have a lot of concepts. So you can see, actually I have about 80 slides, summarize all the important concepts. Starting from the diffraction of light, what diffraction it is. Then we have this resolution, diffraction grating, polarization, and birefrequency. So there are about 5, different concepts you have to understand in this chapter. So I hope everyone of you should try to pay attention here, because today we have to learn a lot of things. So first, what diffraction it is. Okay, so first let me explain what diffraction it is. Then I will highlight the most important formula about diffraction, for you to remember. So what diffraction it is? So you can understand diffraction by comparing light passing through a slit with, for example, you throw a ping pong ball through a wall. Okay, so for example, if you throw a ping pong ball through the wall, right? If you just throw a ping pong ball through the wall, the ping pong ball will just pass through the door without changing its propagation direction. So it will continue to propagate through the wall and just hit the screen once. But the light is doing a different way. If you passing a laser beam through a slot, the laser beam will change direction. So it will no longer just propagate along the straight line and hit the wall once. It will change to other direction. So apart from the central beam, it will also propagate along some other direction, so that you will get a series of bright and dark fringe on the screen. This is called diffraction. So even here we only have a single wall. So you can say if we have a single wall, normally light passing through it, if its direction keep unchanged, it will just hit the screen once, give rise to just a central hotspot, right? But the light is doing a different way. If you are putting a small hole or a small slit here, actually you will see a series of bright and dark fringe on the screen. This phenomenon is called diffraction. Okay, so actually apart from light, other kind of wave like a water wave, if you put a slit in front of a water wave, so it will do the same thing. So for diffraction, you only have to remember one formula. So the diffraction is actually similar to the Young's double slit interference. For example, if we have 2 slits, then passing light through the 2 slits, we will also form a series of bright and dark fringe here. And then for Young's double slit interference, the bright fringe appear when d times sin theta equal to an integer times lambda, right? This is what we learned last week. So d here is the separation between the 2 slits. Theta is the angular position. Okay, angular position. Theta here is just the y divided by the tangent theta is just the y divided by this L. So the angular position of the bright fringe. So that diffraction, will form similar pattern, but the position of the bright and the dark fringe through a single hole will appear in a different way. So for diffraction, you are only require you to understand how to find out the dark fringe position of diffraction pattern. Okay, so for interference of light, you have to find out both the bright and the dark fringe. But for diffraction of light, we only require to find out the dark fringe for the diffraction pattern. So the dark fringe of the diffraction pattern is given by this formula: A times sine theta equal to an integer times lambda. So here are two important things I need to highlight for you, because you can see this A times sine theta equal to integer times lambda. It's very similar, to the Young's double slit interference, right? Very similar to the Young's double slit experiment here. But here I have, three important points highlighted for you. So first, although these two formulas looks different, but they can respond to different things. Okay. So in Young's double slit interference experiment we learned last week, this formula gave rise to the position of bright fringe, not dark fringe. Dark fringe is how much? Dark fringe is d times sine theta equal to a half integer m plus half times lambda. Okay. So it's no longer an integer times lambda for interference. It's half integer times lambda. But for double slit, for single slit diffraction, A times sine theta equal to an integer times lambda. Now give us a position for dark fringe. Okay, give us a position for dark fringe. So first, it can respond to different things. Second, this prefactor A and B are different. In Young's double slit experiment, D refers to the distance between two slits. Distance between two slits. While for single slit, this A is the width of this slit. The width of this slit. Okay, so this is the second difference. Okay, the final difference is for Young's double slit, this M can be any integer from 0, 1, 2, and 4. So it starts with 0. But in this diffraction, N must be a non-zero integer, because N equal to 0 can respond to the position of central bright fringe. Okay. This formula gives us the dark fringe only when N is a non-zero integer. If N is set 0, theta equal to 0 here is the, still the central bright fringe. The other integer N give us the dark fringe. Okay, give us a position of dark fringe. Okay, three difference. Okay. So as I said, in this class, we don't require you to find out the bright fringe. Okay, don't require you to find out the bright fringe. Okay, but if you are interested in knowing how to find the bright fringe, and then you have to refer to this formula. This is not required by our course. This is not required by our course. But I just gave in case some student would like to know, okay, how to find out the bright fringe. So what I do here is light passing through the slit. Actually, its intensity can be just, right by this sine function. Sine function just sine pi x divided by pi x. Okay, so everywhere in apart from the bright and the dark fringe, okay, you can actually find out its intensity, everywhere. Okay, so if you want to find its maximum, okay, bright fringe position, you just differentiate this guy. Okay, some part you will get A sine theta equal to m times lambda. This is when sine function goes to 0. The other diffraction is where you will get the maximum. Okay, so as I said, this is not required, but just for your reference. Now, here comes the most important thing of this part, or most confusing part. I hope every one of you should pay attention to. So the diffraction means when light passes through a very small hole, so it will not just, form an infinitely sharp hot spot. It will have this diffraction pattern. Especially the central bright fringe will have a certain width. So even you passing light through an infinitely, small object, you will get this diffraction pattern. Okay, so this makes every lens system has a certain resolution. So for example, if we have 2-point light source passing through the lens to form an imaging, and then at the imaging plane, you will not see an infinitely sharp. Hot spot, but you will see this diffraction pattern. You will see a finite hot spot, and this finite hot spot has a certain radius. So this makes every lens system have a certain resolution. So for example, if in the very beginning, my two objects are far apart from each other, and then their hot spots, the images they form on the dark plane are well separated. Okay, we can well see, okay, there are two objects. This is when we can resolve the image from the other. But now if suppose we decrease the distance between the 2 points, correspondingly the position of the distance between the 2 images on the image plane will also decrease. Then at a certain position, the distance between the 2 images just equal to the radius of their bright spot. And then at this point, we can still say more or less, maybe there is a still 2 image, okay? So this is when we can just resolve, okay? It's at the boundary whether we can resolve and then or we cannot resolve. But now if we further decrease their distance, when their hot spot completely become to overlap, and then you will no longer tell this is one object or this is one image or 2 images. Because actually, even there are 2 objects, their image completely overlap together, you will lose resolution. You cannot tell actually there is not 2 objects because its pattern is exactly the same as the light emitted by a single point source. This is when we cannot resolve an object. Okay, so this is why we call Rayleigh's resolution. Because of the diffraction, because of light diffraction, any image system like our microscope, right? Like our microscope, it will have a certain resolution problem. So which means, for example, our microscope normally its resolution is limited by about 300 or 400 nanometer. So for example, if we have 2 cells or 2 molecules, when they move in the space, if they are well separated by 3 or 400 nanometer, you will see actually there are 2 molecules or 2 cells under your microscope. But if their distance began to be small when they move very close to each other, and their distance begin to small than this 400 or 300 nanometer, and then you will see there is only one, molecule or one cell under the microscope because you cannot resolve it. So any image system will have its certain resolution. Okay. Now you may wonder what is the resolution? What is the smallest distance? Okay. What is the smallest distance an image system can resolve? So this is what we are going to talk about. Okay. How you can resolve an object only determined by two parameters. One is the wavelength, the other is the feature size of your lens. So for example, if we have 2 point sources S1 and S2, when their distance d or their angular distance theta, okay, the angular distance defined by the physical distance divided by the distance from the 2 objects to the lens. Okay, in this case, my lens here is placed in this hole. Okay, so this is actually the object distance, theta equal to d divided by L. So if this theta is larger than lambda divided by d, lambda is the wavelength, d is the object size, or for example, the diameter of your lens. Okay, and then this is the smallest angular distance we can resolve. So for example, smallest angular distance equal, so the physical distance is just lambda times this L divided by d. So this is L divided by d. Okay, so you can say once your objects are larger than this distance, we are able to resolve these 2 objects. This is what you can see, two images here. But if the distance began to smaller than this value, and then the 2 images will completely overlap, this is when we will lose the resolution. So here, one thing I would like to highlight for you. So for different lens systems, we have different formula. This is for a slit aperture. So for example, here we have a 2-dimensional 2D lens. Okay, so it's a slit. So it's invariant. So which means the geometry is invariant along this out of plane direction. It's a slit. For a single slit aperture, we have this theta minimum equal to lambda divided by d. D minimum lambda L divided by d. But in our normal case, what we use is not a slit 2D aperture. We are using 3D aperture. For example, like a cylindrical lens or a cylindrical mirror, and then you have to times 1.22 in front of this guy. So for example, for circular aperture, like a cylindrical lens, cylindrical mirror, this theta minimum equal to 1.22 times lambda divided by d. D minimum equal to 1.22 times lambda divided by d. Okay, lambda L divided by d. Then before I continue, let me ask you a question. If I want to improve the resolution of my image system, I want to decrease this theta minimum or increase. Any idea? Any idea? If I want to improve the resolution of my image system, whether I should decrease this theta minimum or increase? I want to make my image system better. I want to improve its resolution. Okay, I should make a theta minimum increase or decrease. Student and team, you can type your answer on the chat room. What do you think, student on site? If I want to improve the resolution, I should decrease my theta or increase? Very good. I should decrease. Because smaller theta minimum means I can resolve smaller object. Of course, this is what we want. So if we want to improve the resolution, do remember we want to decrease theta minimum. Because theta minimum or d minimum is smaller, means we can resolve smaller object. Bear this point in mind. I will have an MCQ later to test your understanding about this. Okay. So then the story for what next will be much easier. So if you're passing light through, for example, a grating surface, you will also be able to see this interference pattern, or we also call it the diffraction pattern. So this is actually similar to Young's double slit. So what the grating it is, okay? So grating is, for example, the transmission type of grating, which means my second interface here is corrugated. So it's a lot like what plot in the lecture notes. This figure is what I directly download from the lecture notes in order for your lot to get confused. But you know, the actual plotting is this interface should be corrugated, okay? Should we have a grating corrugated surface on the second interface. This is transmission type of grating. Reflection type of grating, and then the first interface here is a grating. Okay, is a grating. So in your lab experiment doing diffraction grating, we are using transmission type of grating. Okay, transmission type of grating. This is what we will see. Okay. Oh, sorry. Reflection type of grating, the second one. Okay, what I plot here is a reflection type of grating. What you see is a reflection type of grating. Okay, so that if you passing light through, for example, this grating, and then the transmitted or reflected light will also be able to interfere with each other to form a series of bright and dark fringe, you know, on the screen. Then okay, we will be able to determine its bright and dark fringe position. So that for bright diffraction grating, what we require to understand is the position for the bright fringe is d times sin theta equal to m times lambda. This is exactly the same. D here is the grating parameter or the periodicity of the grating. Okay, so it's exactly the same as the Young's double slit. The definition of theta. So first, this is for the bright fringe. D for diffraction grating is the distance between neighboring corrugation, or we say the period, grating period. Okay, theta is the angular position. Angular position, you can diffract. The transmission type is this theta. Reflection type is this theta. Okay, and m's meaning is also the same. So this formula is more or less the same as the Young's double slit experiment. Okay, diffraction grating. So the last concept we have to learn is about polarization. So what's the polarization of light? Okay, so you know, suppose we have certain microscope. If you want to, for example, enlarge the detail of light, see the light's detail, you will find that light is not consists of a number of molecules. Okay, like for example, any object, human beings or desk or computer. If you use a microscope enlarge it, you will find it consists of many particles. So we call molecule or atom. But light is different. If you have a certain microscope that can help you enlarge the detail of light, you will find that actually light is actually this oscillation field. So just like you sweep a rope, okay, just like you sweep a rope. So light is oscillate, in the direction perpendicular to its propagation direction. For example, light here is propagated along the horizontal direction. If you enlarge the detail, you can see actually light is just like a rope wave that is oscillate perpendicular to its propagation direction. Okay, so this configuration is what we call sunlight, unpolarized light, or sunlight or white light is normally this unpolarized light. It is rotated in the plane perpendicular to the propagation direction. But now you can make unpolarized light to be polarized. What do I mean by polarized? Which means now light is not oscillate everywhere perpendicular to the transmission direction. It only oscillates along a certain direction, horizontal or in this case vertical. So you can make an unpolarized light to be polarized by passing it through a polarizer. So that electric field will only be polarized along a certain direction. So for example, if you rotate this by 90 degrees, then the electric field will rotate along the horizontal direction. So unpolarized light passes through a polarizer. So there are two important stuff you have to understand. So first, its electric field will become polarized, only oscillate along a single direction. Second, the intensity will decrease by 1/2, become 50%. Okay, this is one important thing here. The other important thing here is when I passing, so this is what I get when I passing unpolarized light through a polarizer. Now, if you pass a polarized light through a polarizer, something interesting will happen. Okay, so of course, light passes through a polarizer, it will become a polarized light, still linear polarized light. But if the incident light is polarized, intensity will not just be decreased by 1/2, but decreased by cosine theta squared. Okay, decreased by cosine theta squared. This is what we call Maurer's law. Theta here is the angle between the transmission axis, for example, this vertical axis here, and the electric field. Okay, transmission axis and the electric field forms the angle theta, and then light intensity will be decreased by cosine theta squared. Okay, cosine theta squared. This is what we call Maurer's law. So you can say if light electric field is just along the transmission axis, and then its intensity can remain unchanged, completely unchanged. But if it's perpendicular to it, okay, and then there is zero transmission. So for example, here I put another polarizer here along horizontal, because the original light polarization is vertical. Now this is horizontal, okay, so that they form a 90-degree angle. There is zero transmission on this side, okay, because of the Maurer's law. So another important issue you have to understand is apart intensity decreased by cosine theta squared, the electric field of light passing through the polarizer will also change to the direction parallel to the transmission axis, okay, parallel to the transmission axis. Originally, for example, light along the horizontal direction, and then there is a polarizer, its electric field along a certain degree with respect to this vertical direction, and then its electric field will also be rotated to the corresponding direction. Okay, this is another important stuff you have to understand. So apart from passing light through a polarizer, we can get a polarized light. You can also get a polarized light by passing light, through, for example, ND interface. Okay, so so suppose here we have a material with a certain refractive index. Its incident, unpolarized light incident upon the material. So here we first have the plane of incidence, which is perpendicular to this interface. So for the plane of incidence, unpolarized light will have electric field either perpendicular or in parallel to the plane of incidence. So normally we use dots to denote the electric field perpendicular to the plane of incidence. This is what we call S polarized light. And this double arrow to denote light with electric field parallel to the plane of incidence. This is what we call p-polarized light. So unpolarized light consists of both S and P polarization. So it's given by this both dots on a double arrow. So what people, so actually is called Brewster found that if you insert the unpolarized light onto the interface at the right angle, then the reflected light, as I said, at the right angle, then the reflected light will be completely S-polarized. This is what Brewster found, okay? So this is the second way for us to get polarized light upon incident at the Brewster angle. The Brewster angle is defined as tangent theta p equal to N2 divided by N1. Okay, N2 is the refractive index at the transmission side, N1 is the refractive index at the incident side. So once light incident at this angle, the reflected light will be completely S-polarized. Okay, but transmitted light still consists of both components, okay, P and S, but the reflected light is completely S-polarized. This is what we call Brewster angle. So an interesting thing for Brewster angle is, okay, at the Brewster angle, the reflected light beam and the transmitted refracted light beam here are perpendicular to each other. Okay, reflected and the refracted light are perpendicular to each other. Okay, so this is for Brewster effect. So the final thing is birefrequency. So what birefrequency is, okay? So you know, in nature, most of the material will just have a single refractive index, like glass, right? Water, it has a single refractive index. So no matter for S and P polarized light, it will see the same refractive index. But in nature, we have another class of material called birefringent material, such as calcite, quartz. So this kind of material will have two different refractive index for S and P polarization. Okay, for S and P polarization. So if we have unpolarized light incident upon this kind of birefringent material, because S and P polarized light see different refractive index. You know, refractive index determines how light will be refracted into the material. So that S and P polarized lights will be refracted in different way because they see different refractive index of the material. So that it will make S and P polarized light to be separated. So here, the P polarized light in the birefringent experiment is called extraordinary ray, while S polarized light is called ordinary ray. So once an unpolarized light passes through the calcite crystal, so the E and O ray will be separated. This is what we call birefringent. So for birefringent, there is one important thing for you to remember is, okay, normally what people will ask, if unpolarized light passes through, for example, birefringent, what is the phase difference introduced between E and X-ray, or what is the optical path introduced between E and X-ray? So that is given by this formula. The optical path difference is just the difference in their refractive index times the thickness of the calcite slab. Corresponding phase difference is 2 pi lambda. 2 pi divided by lambda times this optical path difference. So it's actually 2 pi d divided by lambda naught times Ne divided minus No. So this is the optical path difference and the phase difference introduced when light passes through a slab. Okay, so these are the all summaries. Any questions? So if no question, let's look at the tutorial solution. Okay, here I have 9 questions. You know, 5 tutorial and 4 past examination papers for you to strengthen your concept. So first, let's consider light with a wavelength given by this number illuminates a single slit whose width is 0.75 in millimeter. At what distance from the slit should a screen be located if the first minimum in the diffraction pattern is to be 0.85 millimeter from the central screen? What's the width of the central maximum? Okay, so 2 parts. Let's look at it one by one. So first, can you tell me, this tells me what concept of light? Interference of diffraction. Clearly it's diffraction, right? First, there are some keywords. As I said, when you solve past examination paper, do identify some keywords. First, there are single slit and a diffraction pattern. Okay, so this clearly give us to single slit experiment. So for single slit diffraction, we only learned one formula. So that is this A times sin theta equal to M times lambda. Okay, this is the only formula we learned about single slit diffraction. So in the future, if we do that, when you do the final examination, if you find this question is difficult to, for example, don't know how to start, as I said, what you do is first identify the correct keywords. Because once you identify the correct keywords, know what this question asks you to do. Normally, there is only one or two equations for you to apply. That equation will normally be provided in the formula sheet. So once you put that right equations under the question, even you have not solved, till the end, you will still be given mark. So for example, in this case, we identify this as single slit diffraction. We first write down this formula, A times sin theta equal to N times lambda. This is the only formula we learned here. So of course, we should write it down. Now, let's look at what this question talk about. This question talk about we have a single slit. A here is 0.75 millimeter. When light passing through it, okay, its first diffraction pattern, the first minimum, so which is the first dark fringe, right? The question said first minimum. First minimum is the dark fringe. First dark fringe is the first dark fringe y1 equal to 0.85 millimeter. 0.58 millimeter. So what I want you to do is to calculate this d. Okay, as the question said, at what distance should the slit be? Should the screen be located? Okay, should the screen be located? Is we found out this distance d. We found out this distance d. You can say for this is equal to 0.85 nanometer. Okay, if you directly apply this, for first dark fringe, which means m equal to 1, right? So you can say A is given, M is given, lambda is also given. What we can do? We will be able to calculate theta, right? Once theta is known, tangent theta equal to y1 divided by d. Y1 is given, so that we will be able to get d, right? So this is the idea. So first, from this question, from this formula, we will be able to get the unknown parameter theta, and then from theta we are going to calculate d. So be very in mind, actually the d is normally in meter, and the y1 is in millimeter. So d is much larger than y1. So that sine theta is actually approximately equal to tangent theta. Okay, which is y1 divided by d. Y1 divided by d. This formula gives us sine theta. Sine theta is also y1 divided by d. So that you can, if you replace sine theta by y1 divided by d, you can get a times y1 divided by d equal to lambda. AD lambda is also given, so that we only need to calculate, or A y1 lambda is given. Then we can rearrange this equation to get what b it is. Okay, so it's about 1.09 meter. Any question? Any question? So no question. So let's look at the second part. The second part asks what's the width of the central maximum. The width of the central maximum actually measures from the two neighboring minimum. So it's this minus y1 to positive y1. So clearly the width is just a double y1. Okay, so that is equal to 1.7 in millimeter. So this actually tests you some schematic understanding of the concept. You don't have to do any mathematics. Okay, you don't have to do any physics. The mathematics is quite easy. Okay, just twice y1, 1.7 millimeter, which is quite straightforward. So now before I continue, let's look at this past examination paper test last year. Okay, so here I have light at a wavelength 605 nanometer passes through a double slit, as shown in this figure. The two waves after the slit arrive at point P on the screen. What we know is the accumulated phase difference of the two arriving waves is measured to be 1 in radian. determine the slit separation and the location of the first bright fringe on the screen. So actually, this is Young's double slit interference. So actually, we should talk about the next week. I don't know why this question is given in this, in this tutorial. But anyway, let's look at it. So it gave us, for example, the wavelength. It gave us a wavelength. It gave us an optical pulse difference. Want you to get what is D? What is D? Okay. So that for Young's double slit. Okay. So first, it gave us an optical pulse. So as I said, for optical pulse, what you have to give us the phase difference. As I said, phase difference is always related to what? Related to the optical pulse difference. 2 pi divided by lambda times the optical pulse difference is actually the phase difference. Okay, 2 pi divided by lambda times the optical pulse difference is the phase difference. So that R2 minus R1 is delta L. So we learned last week. In Young's double slit, this R1 minus R2 or phase difference is always equal to D times sine theta, right? Delta L equal to D times sine theta. In thin film experiment, delta L equal to either 2nt or 2nt plus half lambda. But for Young's double slit, this delta L can only be equal to delta times or just equal to D times sine theta. Okay, from this question, what you can see, delta phi is given, 2 pi is of course, lambda is also given. Lambda is also given. Theta is measured in 1 radian. So that rearrange this equation, you will be get what D it is. Okay, D just equal to lambda delta phi divided by 2 pi sine theta. Okay, 2 pi sine theta. Oh, sorry, delta phi is measured in 1 radian. Sine theta has to be calculated from this configuration. Okay, you look at this right angle. P here is 0.01 millimeter. This is 2 meter. So that you can say theta is small. So that my sine theta is approximately equal to tangent theta. My sine theta is approximately equal to tangent theta equal to this guy. So that I just replace sine theta by tangent theta. So which is this one, I can get what D it is, which is about 20.7 in millimeter. 20.7 in millimeter. Okay. Theta is calculated through this right angle. So once theta is given, the second question wants us to calculate where the bright fringe should appear. As I said, the bright fringe is always equal to m lambda L divided by D. Okay, m lambda divided by D. As I said, try to remember this formula. This is also the separation between neighboring bright slits. Okay, so if you just substitute lambda L and D into this equation, you can get, okay, my Y, where the first bright fringe happens is 0.063 millimeter. Okay? Any question? Any question? Okay, if no, let's continue. Okay, so this is a very difficult question. Okay, also about Tesla 2 years ago, also about the interference of light. It's actually why it's difficult because it's a combination of the single slit diffraction and the double slit interference. So what this question said is, okay, we have three screen located in this way. The first screen is single slit with a width equal to 0.1 millimeter. So when light passing through it, it will of course form a diffraction pattern on the second screen. The second screen is actually a double slit screen. Its double slit is just located in such a way that the distance is the center from one slit to the center of the other slit. Okay, and this double slit, their width just equal to the width of the first dark fringe, the bright fringe. This is a zero-loss bright fringe. These two are the first bright fringe. Okay, and their locations, just located, at the first dark fringe. So where their two ends exactly overlap with the first and the second dark fringe position. Okay. And then of course it was the two slits located at the bright fringe, so that the bright fringe slide, so the light located here can passing through this two slits. and then form an interference pattern. So it's first a single slit diffraction, and then afterwards we have double slit interference. Okay, we have double slit interference here. So what we know is the original here is 0.1 millimeter. 0.1 millimeter. And then this D remain unknown, but of course we can use the diffraction property to get what is D. But what this question asks us to find is the space between adjacent bright fringe, which is this D prime. So again, what is the for interference? What is the distance between neighboring bright fringe? I ask everyone of you to remember. How much? Lambda L divided by D. Okay, again, delta L is just lambda L divided by D. Okay, try to remember. Okay, so what we have to determine, okay, is actually what this D. If this D is known, lambda times this L, distance between the two siblings, lambda times this L divided by this D will give us D prime. So actually this just asks us to find out what is D. You can say D is actually the distance between the center of the two slits. Once we will be able to find out, for example, the first and the dark fringe position, we will be able to find out where the center of the slit is located. And then twice of this y coordinate is actually D. So actually this is the idea. So how we should calculate this D is to using the diffraction, As I said, for single slit diffraction, the first important thing we should do is write down this formula: A sin theta equal to an integer times lambda. Okay. Once you write down this, you will be already awarded the mark. Then we use small angle approximation, replace sin theta by tangent theta, which is y divided by d, so that you will be able to get A times y divided by d equal to an integer times lambda. So that the dark fringe position for single slit is given by an integer m times lambda times d divided by A. As I said, these two are the first and the second dark fringe, so that we set the n equal to 1 and 2 respectively. This corresponds to n equal to 1, this corresponds to n equal to 2, so that you will be able to get the y coordinate for the first and the second minimum in the diffraction pattern. Okay, the center's y coordinate is just y1 plus y2 divided by 2, right? y1 plus y2 divided by 2 is the y coordinate from the center to this dashed line. Of course, b is just twice of this distance. So which means my d is actually y1 plus y2, which is about 3.18 centimeter. 3.18 centimeter. So as I said, the final d prime, so is delta y. The distance between neighboring bright fringe is just lambda L divided by d, so that we already get d. Lambda and L are given in the question, so that we get my delta y is 1.67 times 10 to the minus 5 meter. Okay, clear? Any question here? Any question? Okay, no question. Let's continue. So now this comes to the problem about resolution. Okay, so what this question tells us is when Mars is nearest to the Earth, okay, the distance between the two stars is separated by this distance. Okay, this is in kilometer. Okay, now the Mars is viewed from a telescope. The telescope is formed by a concave mirror, and the diameter of this mirror is 30 in centimeter. If the wavelength of the light used is 590 nanometers, so this is typical yellow light, okay? Blue, between yellow and red, okay? What's the angular resolution of the telescope? Then what is the smallest distance, so which is physical resolution? That can be resolved on the 2 points on the star. So first, what we learned from, for example, my summary notes is, okay, for single slit aperture or circular aperture, the angular resolution is calculated in different way. So first, from the information given in this question, can you tell me what we are looking at is a single slit aperture or a circular aperture? Sorry? Very good. Why? Because it tells the diameter. Okay, diameter can only be assigned to a circle. Okay, this is what you should understand. Okay, so actually normally when resolution is tested, 90% we are testing circular aperture because circular aperture is what we have in experiment. Single slit is seldom used. Okay, so actually I think this formula is much more often used. Okay, so you can say what is the angular resolution? If you identify the circular aperture, you directly write on this equation. You write on this equation, you can say lambda is given 590. A is also given diameter 30. So actually all the parameter is already known, in this equation. You can directly, calculate the angular resolution. Okay. So although the resolution is actually a difficult question, okay, it's quite confused. But what I mean is in the final examination, we normally ask you to directly apply the formula. Because lambda and will also be given to you. So for this question, because lambda and d is given, then you directly substitute into the equation, you can get what the angular resolution it is. 2.4 times 10 to the minus 6. Then, as I said, the angular resolution and the physical resolution is related by this formula. Theta minimum equal to d minimum divided by L, the distance between the lens, the aperture, and the object. So that d is just equal to L times theta minimum. So it's 2,230 kilometers. So which means if you use the microscope to say, for example, 2 persons on Mars, then if their distance is larger than this guy, you will say they are well separated. Otherwise, the image of the 2 persons will exactly overlap. You will see them as one. Okay. So this is what this question asked for. Any question? Any question? So now, as I said, in order to, for example, now this is the angular resolution. As I said, in order to improve the resolution, what we should do is decrease theta, right? So if I want to decrease theta, how many ways are there? How many ways can we decrease theta? Any idea? Student team? How many ways can we increase the resolution? Give me an answer. Hello?
Beta or lambda?
Yes, very good. So what we should do is actually there are 2 ways. Either decrease lambda, right? Decrease the wavelength, or increase this aperture size d, right? There are 2 ways for us to improve the resolution. Either make lambda smaller or make d larger. Then bear this in mind, let's consider, okay, one question. Okay, so there is actually, before we consider this MCQ, so there is one past examination paper test about, 4 years ago, okay, which is more or less the same as our tutorial here. So you can take a look yourself. I already provided the solution here, okay? So now, everyone take a look at this question. So I already did this question on learning catalytics. So that with this session number, please try to solve it. I give you 2 minutes. 2 minutes. Okay, take a look at this question. So what I want to do is here I want you to use color filter to increase the resolution and ask you which color should I use. Yeah, hello, try to submit your answer. Take a look at this question. Session number already provided here. Yeah, just half a minute left. Try to submit your answer. Okay, thumbs up. So as I said, in order to improve the resolution, we should either increase lambda or increase d. So using color filter, we are actually operating on the wavelengths. So that we should choose the smallest lambda. So among these four colors, blue light has the smallest wavelength. So that we should choose A. We should choose A. So of course, if there is another solution, for example, violet light or even ultraviolet, we should choose that one, okay? Ultraviolet, okay, because it has a even smaller wavelength. So yes, there is another question test about 3 years ago, but I don't have time to go through. Also about the differential. You can see differential actually tested quite often in the final examinations. So okay, so I hope every one of you should try to you know at least understand this, especially the combination of it with the resolution. Okay, so now let's take a look at question 3. So here we have 3 polarizing disks, okay, polarizer. They are parallel to each other and they are all centered on the same common axis, the same straight line. This is the direction of their transmission axis. The first one is, transmission axis located at theta degree with respect to the vertical. So for the second and the third one is theta 2 and theta 3. Okay, theta 2 and theta 3. Now I have a plane polarized beam with electric field parallel to the vertical direction incident upon the leftmost screen. The intensity of the original light is 10. I want you to calculate what is the transmitted light intensity if theta 1 equal to 20, 40, and 60 degrees respectively, or if theta 1 to theta 3 equal to 0, 30, and 60 degrees. Okay, so this question have 2 parts. Let's look at it one by one. So clearly, this is a thin polarized light passing through a polarizer. Polarized light passing through the polarizer, okay, what you identify, okay, is polarizing axis, and then we only learn the one formula. That is another one. So unpolarized light passing through the polarizer is always decreased by 1/2. But polarized light passing through this polarizer, okay, it will be decreased by cosine theta squared. So that you can see clearly you can find out the relationship between I2 and I, incident I here. So my I2 should equal to my incident light intensity times cosine theta 1 squared. Okay, cosine theta 1 squared. Now, for the second polarizing disk, okay, I2 is now the incidence. I3 is the altitude. Now let me ask you the question, what's the relationship between I2 and I3? So I3 should equal to I2 times how much? Should it be cosine theta 2 square or something different? So any idea, student team? What I'm asking is what's the relationship between I2 and I3? So should I3 equal to I2 times cosine theta 2 square or something different? What do you think? Now, what we should do is trying to find out the angle between the incident light and the transmission axis of the polarizer. So what's the direction of I2? What's the electric field's direction for I2? Any idea? Student team? So let me remind you for the polarizer disk, okay? When light passes a polarizer, at the output, the electric field will be automatically oriented along the transmission axis of the polarizer. So that for I2, the electric field should be along this theta 1 direction, okay, theta 1 direction. So you can say I2 is electric field along theta 1 direction. The transmission axis for the second polarizer is theta 2. Then what's the angle between the electric field for I2 and the transmission axis for the second polarizer? What's the angle? What's the angle? Student team?
Theta 2 minus theta 1.
Very good. Should be theta 2 minus theta 1. So actually my I3 should equal to I2 times cosine theta 2 minus theta 1 square. Okay, cosine theta 2 minus theta 1 square. So the same for I3, its electric field will not be oriented along theta 2 direction because, as I said, once polarizer light passing through the polarizer, apart from the decrease in its intensity, its electric field will also be changed to the transmission axis direction. So I3 will have the electric field along theta 2 direction. So that it forms an angle theta 3 minus theta 2 with respect to the transmission axis of the last polarizer. So that my final output IF should equal to I3 times cosine theta 3 minus theta 2 squared. Okay? So that I just substitute I2, I3 by I2, I2 by II here, I can get this guy. So my final IF equal to 10 units, which is I, the original incidence, times cosine 20 degrees squared 3 times. I get 6.89 units. Then I do for the part B. Part B is just the theta 1, theta 3, and theta 2 are put in a different way. So theta 1 equal to 0, so that I times cosine theta 0 squared. This is 30 minus 0, 30. 60 minus 30, also 30. So that I get 5.63 units. So you can say for both cases, theta 3 is 60, okay? For both cases, theta 3 is 60. So which means the final output light electric field are oriented on theta 3. So the final output light is electric field's direction are the same. But because the polarizer are put in different way or output are different. Now I give you an important conclusion. If you want to rotate the light by a certain degree, I give you a number of polarizers to do that. So you can maximize the output light intensity by make the polarizing axis of the polarizer equally spaced in the angular direction. So for example, here I have 3 polarizers. I want to rotate the light electric field by 60 degrees. So actually I should put the around 20, 40, and 60, so that each of the neighboring polarizer, their angular position is 20 degrees. This will maximize output. If you are not put along the equally spacing, and then the intensity will be minimum. Okay. So this is one important conclusion. Okay, when the transmission axis of the polarizer equally spaced in the angular direction, and then we will maximize the output. So bear this conclusion in mind. I will have a tutor. I will have one question, additional question for you to consider, after the class. Now, before we look at this problem, so let's, take a look at this guy. Okay, this is another MCQ. So try to solve it. I just deliver this question on learning catalytics. Okay, on learning catalytics. So that try to submit your answer again within 2 minutes. Okay, take a look at this one. Last 20 seconds left. Try to submit your answer. So thumbs up, you can continue, submit your answer, but here I can show you the solution. Okay, so what we do is we use I times, cosine square 45 degree. Cosine square 45 is actually 1/2. Okay, and then for the second polarizer is actually theta 2 minus theta 1 cosine of that angle square. So that the final answer should be 1/2 times 1/2 equal to 1/4. We should choose B. Okay, we should choose B. Any question? Any questions? Still nothing? Hello? So if no question, okay, so this is my additional, question. Okay, so now instead of have 2 or 3 polarizer, here I have a series of 5 polarizer. Okay. So that I set my output angle theta 5 equal to 60 degrees. So which means I still want to rotate. The incident lines electric field by 60 degrees. Now what I want is I want to maximize the output IF. I want you to determine why at what angle theta 1, theta 2, theta 3, and theta 4 should be orientated, so that I can get the maximized output. And what is the maximized intensity? Okay, try to look at this question. Okay, I will show you the solution next time. So bear in mind, what I do is if we want to maximize the output, all the polarizer, the transmission axis should be equally spaced in the angular direction. Look at what does that mean. Okay, so this is one of the question on the length, so that we will quickly get through of that. So that another question I would like to let you know is actually you can do the polarization experiment actually directly use your computer. So for example, with this your computer screen, this liquid crystal screen, the emitted light here is actually linear polarized light. Linear polarized light, but the electric field is just 40 degrees with respect to the horizontal and the normal. Okay, so this is the experiment I do. Okay, I just borrow a polarizer through the light. So first, rotate it to, so this is the transmission axis of the polarizer, 40 degree with 45 degree. 45 degree with respect to the horizontal and the vertical, so that you can see maximize the output from the computer screen. But now look at what will happen if I rotate the screen. If I rotate my polarizer, whether I will be able to control the intensity. Look at this video. Now I rotate it counterclockwise. You can see it become dark, dark, and darker. Then minus 45 degree, completely dark, completely block the light. Then I rotate it back. You can see the brightness will increase and the maximum brightness, and then again to another 135 degree, I get totally dark. Okay, so this is actually an experiment we can do. Borrow a polarizer in the light, put it in your computer screen, rotating it, you will see, okay, the changing of the transmitted light. So there is one question tested 4 years ago about polarizer, but again, I don't have time to go through this. You take a look at the solution here. So if you have any question, let me know, okay? So yes, another question, yes, 4 years ago on polarizer, okay, take a look yourself. Solution provided. So now let's look at tutorial question 4. Now we have light striking a water surface at the polarizing angle. Okay, polarizing angle is a Brewster angle. So clearly this question is test about the application of the Brewster formula. Tangent theta T equal to N2 divided by N1. Okay, the part of the beam refracted into the water strike a submerged glass plate, as shown in the figure below. If the reflected light from the upper surface is completely polarized, what is the angle between the water surface and the sun? So what is the angle theta here? Is what this question asked for. What is this question theta here? So clearly the question said, okay, the first angle is a Brewster angle. We can quickly use Brewster effect to find out what my theta p it is. Okay. So the second part of this question, light reflected from the upper surface of this slab is completely polarized. What does this mean? Any idea? What does this question mean? If this light here is completely polarized, what does this mean? So which means the incident is what angle? Any idea? How about student online? The reflected light is completely polarized here. So this angle should be what angle in order for the reflected light to be completely polarized? Any idea? Student online? What do you think? If I want my reflected light to be completely polarized, what angle should I incident? What should be my incident angle? Clearly, this is Brewster angle. Again, another Brewster angle. Why? Is because only at the Brewster angle, the reflected light can be completely polarized. This is what I highlighted in the summary slides. So that in the future, if you see in the question, for example, keywords like polarizing angle, Brewster angle, or most importantly, if you say the reflected light is completely polarized, all three cases can respond to incident at Brewster angle. Okay, let me repeat. In the final examination or in your quiz, if you say some keywords like polarizing angle, incident at the polarizing angle, or incident at the Brewster angle, or the reflected light is completely polarized, that all means the incident angle is the Brewster angle. You should apply tangentially the incident angle equal to N2 divided by N1. This is asking you to use tangent theta 1, theta I equal to N2 divided by N1 to find out your incident angle. Okay. So for this Weber question, which means the first angle theta p is a Brewster angle. The second angle again is also the Brewster angle. So that I want you to find out this theta. So to find out this theta is actually very easy now, okay? So that we just try to look at this triangle, okay? Put it down, this triangle here. So that if we will be able to find out this angle is actually the reflected angle theta 2 plus 90 degree, theta 2 plus 90 degree. And this Weber angle, remember this is surface normal, equal to 90 minus theta 3, 90 minus theta 3. So theta 3 is the incident angle. Once we will be able to find out the reflected angle at the first interface and the incident angle at the second interface, we will be able to find out theta. Now let's do that one by one. At the first interface, theta p is the Brewster angle. So that my tangent theta p should be equal to n of the transmitted side divided by n of the incident side. So at the transmitted side is water, incident side now is air. So that is n water divided by n air. I get my theta p is about 53 degrees. Once I get a theta p, of course, incident angle, I can calculate what my theta 2 is. Either use the Snell's law, I can get about 37 degrees, or I use the property at the Brewster angle, the reflected and the refracted angle are perpendicular to each other, so that my theta p plus theta 2 equal to 90 degrees. I can also get my theta 2 equal to about 37 degrees. Okay, now theta 2 is given. Then for theta 3 is now at the Brewster angle. Can you tell me my tangent to theta 3 should equal to how much? What's my tangent to theta 3? Is it still n water divided by n air, or something different? My theta 3. My theta 3 should equal to how much? Tangent theta 3 equal to how much? Any idea? Still nothing. My theta 3, tangent theta 3 should equal to how much? Very good. Should be n glass over n water, because is the reflective index of the transmission side divided by the reflective index of the incident side. Now I am incident from water to glass. So that should be n glass divided by n water. So that I can get my theta 3 is about 48.4 degrees. 48.4 degrees. So you can say once my theta 2 and theta 3 is given, I can calculate theta, because theta plus this angle, theta 2 plus 90, plus another this angle, 90 minus theta degree, then equal to 180 degree. 180 cancel out this 290, I can directly get my theta is equal to theta 3 minus theta 2. So which is 11.5 degree. 11.5 degree. Okay? Any question? So no question. Let's so there is a question 3 years ago, more or less the same as this tutorial. So take a look at yourself whether you can solve this question by your own. So there is another question, tested in semester 2, 2019. I think this is a typical question, testing some concept. This is why I want to talk about this one. So here I have a sample of material with refractive index given by this one, 1.45, okay, in air. So this is a slant, optical fiber. So that, of course, N2 outside is N equal to 1. The sample has a slant interface with an angle alpha here. So that light incident onto this surface is equal to the Brewster angle. So Brewster angle, which means my theta b here, tangent theta b should be equal to how much? N1 divided by N2 or N2 divided by N1. Brewster angle keyword. So of course, apply the Brewster law. Then my tangent theta b should be equal to how much? N2 divided by N1 or N1 divided by N2? Any idea?
N2 divided by N1?
Yes, should be N2 divided by N1. Always transmission side divided by the incident side. Okay, so this is actually the first question. So you can say once you get tangent theta b, you can say this is alpha, this is also alpha. Alpha plus theta b should equal to 90 degrees. You will be able to get what alpha it is. This is the first question, okay? If there is low transmission of the incident light from the sample towards L, what is the polarization state of light? Low transmission, okay? So now let me ask you, low transmission, how can we get low transmission? Low refraction, right? So that means total internal reflection. So that we will get low transmission here. If it's total internal reflection, there is no transmission. So are there any polarization criteria on total internal reflection? This is a question I would like to ask you. Are there any polarization requirements on the total internal reflection? Good, no, or answer is no, so that you should say, okay, there is no polarization requirement. No matter is S or P polarized light, as long as this is total internal reflection, it will be no transmission here. So this is our answer. So as I said, what we do for the question 1 is first find out my theta b, tan theta b equal to N2 divided by N1. So we get theta b equal to about 34.6 degree. Alpha lighting minus theta b, so that I get alpha. Solution to the second question, low transmission is expected, which means total internal reflection. Total internal reflection does not have any requirement on the polarization, so that the incident light can be any polarization. Okay? Any question? So if no question, let's look at the final one. The final one is about birefringence. Okay, the final question is about birefringence. So which means now here we have a birefringence slab. Now I passing through unpolarized light into this slab so that E ordinary light and extraordinary light will see different reflection index. The first question asked us to show that, okay, when you passing unpolarized light through the slab, the phase difference introduced between ordinary and extraordinary light is given by this equation. And then B, in a particular case of quarter wave plate, light passing through the slab will introduce a phase difference pi/2 for E and ordinary, for ordinary and extraordinary light. I want you to find out what is the thickness D for the quarter wave plate. What is the wavelength D for the quarter wave plate? So this is the configuration, okay? So one light here, so one will say one reflective index, the other will say the other reflective index. Once it passes through a thickness with D, what will be the phase difference? So actually this question is quite easy. It tells you apply the relationship between phase difference and optical path. Okay, so the phase and optical path have this relationship 2 pi divided lambda times L. So that for ordinary light, okay, then 2 pi times lambda divided by L. This L is optical path. So for ordinary light, L naught is just equal to NO times D. N ordinary times the thickness, because the optical path is fixed at D. The same for ordinary and extraordinary light. The only difference is the reflection index. So that we replace this L by NO times D for ordinary light and NE times D for extraordinary light. Minus them together, you can get, okay, is exactly what this question asked for. Quite easy, right? The second part is even easier. You just set this guy to pi divided by 2, and then you will be able to calculate what is D. So, in the future, if you say some question, especially in the final examination, which you found, okay, somehow you don't understand it, don't be afraid of, the many description there, because it normally asks you to directly apply a certain formula. So take the part 2, for example. If you directly equal the question given in the question, so the formula given in the question, to this pi/2, you can already solve it. Because lambda is given, NO, N is given, and then you can directly calculate what is D. So this is what I would like to highlight for you. In the final examination, maybe there will be a long description of a certain question, but that question can be very easy. And normally the different part have different, they don't have any relationship. So if you don't know how to show, but you can still solve for B. So that in the final examination, do remember that you go through all the questions each time. If you find, for example, part A is difficult, also look at part B and part C. Because part A and part C may be even easier than A, and you don't need to apply any knowledge in A in order to solve B and C. Okay? So this is that thing I give to you. So this will be the end of my class. Remember, we have consultation session every Friday afternoon. So that if you have any question, so you can still remain here. So I will do the consultation and discuss with you. Otherwise, the class can be dismissed.